Hello, my name is Ever Barbero, and today I want to talk about notch blunting. This is video number 2 for stress concentration in chapter 5, failure. Okay, so just a review of the previous video, number 1 for this series. If the material remains elastic, there is no plasticity, then the stress peaks near notches, and that's why we need a stress concentration factor. And that could be a lot, okay? Then stress concentration can be calculated easily by using charts, although in video number 1 we use finite element analysis, but that was just to produce pretty color plots. But for this class and for preliminary design and for fast, reliable calculations, we use mechanics of material formulas and a stress concentration factor from charts. All right, so you've seen this picture before. This is the finite element analysis model for the bar with a hole, where we identify the stresses and we check that those stresses coincide with mechanics of material formula, like for example, the nominal stress. Then we calculate here 100. And the net stress, we calculate here 200, and we identify these points. That's all in the previous video. And so we gain confidence that the model is doing the finite element analysis is doing the right thing. And then we go look here, and we say, oh, the maximum stress is 434. Oh, how can be 434 magnified 200? That's 2.2 times. That is a stress concentration. So that's what we mean by stress concentration. All right, so how do we handle this without doing finite element analysis? Well, we calculate the net stress and we multiply by the stress concentration. And the stress concentration factor, where do we get it? We get it from this chart. Here it is, KT. And the chart gives us these values for different geometries. That is ratio, diameter of the hole versus the width of the plate. All right. And so we get this number, and with that we get the maximum stress. And for this case, we predict 438 and finite element predict 434. So identical, basically. Okay, so now let's talk about brittle versus ductile materials. All right, so the picture that we've seen before, like this picture, the stress can go so high because this was done in the elastic regime. True, then this stress is 100, this is 200, and this is 434. And it's a real material, so it's not a made-up material. It's a material that we use in homework 1 to do the analysis of the materials. So, okay, so now we know that the stress will grow if the material is elastic. Now we talk a little bit about the type of load. Quasi-static load is a load that is applied once or a few times, and then held constant. So it's not a load that we are changing all the time, like repetitive, cyclic, alternating, or fluctuating. These loads are for chapter 6, fatigue. So if the number of load application is small, or the material is insensitive to fatigue, because there are materials that are insensitive to fatigue, so it doesn't matter. They don't care about fatigue. Then even a repetitive load can be assumed to be quasi-static. But in general, when we say quasi-static, we mean a load that we put and we leave there, or we put only a few times, not many times. And why we say quasi and static? Because we cannot really put a load statically, completely, because static is that we don't do anything. And we had to do something to put the load. So that's why it's called quasi-static. So now, if the load is quasi-static, the stress concentration factor applies only to brittle materials. How come? We're going to explain in this video. Ductile metals are insensitive to stress concentration factor, all right? And unless the load is fatigue load. But if it's not fatigue load, then ductile metals are insensitive to stress concentration factor. And we will explain this now. So in order to explain this, we're going to use this example. This is a bar under traction with a fillet. The fillet has radius r. It starts at large d, reduced to smaller d. And we know that if we go far from the stress razor, this is the stress razor here, the fillet. If we go far from it, Then we can calculate the stress accurately with mechanics of material, P over A. Sigma 0 is P over A, where A is the area net. That is this area here. And this stress is uniform if we are far from the stress razor and also far from the point of application of the load. So here in the middle of this bar, we have this stress, but we know that this stress will be magnified over here if the material is elastic, and we will get sigma max. So this value sigma 0 we can calculate as P over A. A is little d multiplied by the thickness. And sigma max we can calculate as KT from the chart times sigma 0. Okay, that we all know that. We know all that from the previous video. Now for this discussion, we're going to assume a material with S of y equal to 40 KSI, and it's ductile. If it has S of y, that means it's ductile. All right. So okay, and this is like an experiment, but a made-up experiment. All right. So here on the right, we have a chart of stress versus strain, right? Like in homework 1. We apply a stress and we measure the strain, or we apply a strain and we measure the load divided by the area, we have the stress. And if we go on this blue line, that will be the elastic material that has a model of elasticity E, which is the slope of this curve. Everybody knows that. So now for this discussion, we're going to assume that the area is 1, so that sigma 0 is directly P. From this equation, sigma 0 P over A, I put A equal to 1, so sigma 0 is P. And then stress concentration, I'm going to assume is 2. And of course, SY is 40, and it's ductile. So here we go with the loading program. So first I load to point A. Point A is here. And I put a force of 10, which produces a sigma 0 of 10, multiplied by the stress concentration factor 2, that becomes 20. That will be the sigma max. So that means that the stress at the root of the notch of the fillet is supposed to be 20. And so I get this stress 20. On this line, I went up to here. The stress is 20, and I went up to here. Everything's good, right? Okay, so now I'm going to put double the load, 20. Sigma 0 is 20. KT sigma 0 is 40. Sigma max is 40. And now my safety factor is 1 because if I go to 40 in stress, I'm at this point and I'm just almost barely yielding. Okay, a little bit more and I yield. I'm right there. So safety factor is 1. Oh, everybody okay? So now comes the interesting part. Now I put a force of 30. Sigma 0 is 30, KT sigma 0 is 60, but wait a minute. I cannot go to 60, yes? Because the material yields and it does this, all right? And we can approximate the material as elastoplastic, meaning that, okay, I could do it exactly, but it's easier to do the example, assuming the material just yields and the stress is constant and S of y. But even if it's not constant, it grows a little bit, even not that much. But to 60, I cannot get there, right? No material that is ductile will take you to 60. It's impossible, all right? And now this elastoplastic model, where you go like this and then flat, is a useful model to solve problems of crashworthiness and other problems, where you don't want to deal with this curve, which complicates your solution. We're not going to do this, but I'm just telling you, this is not just something I made up. It's very common to assume the material is elastoplastic, and it's a good approximation. A lot of stuff has been designed with this approximation. So, but anyway, so that means when I put 30, the stress should be 60, but it can't. So I'm going to keep it at 40, elastoplastic. If you want, put it at 41, I don't care, but it's not going to go to 60, right? Impossible. So my safety factor, I put this equal to 1, all right? And then, well, to exaggerate, I'm going to put a force of 40. That means that the KT sigma 0 is 80, but the sigma max, no, it's going to be 40, 41, no more than that. So, all right, so that means that you put whatever force you want, you cannot go up this way because the material is not elastic. Yes, the material is elastoplastic or plastic at most, okay? So this is very important, and it's very important, and this is the reason why ductile metals are so popular to make everything, all right? So let's emphasize this, all right? So let's say we have the fillet, and we put a sigma 0 10, that means load 10, sigma 0 10. The stress magnified by stress concentration is 20, no big deal. 20 is less than SY, so you can take it. This is elastic. You see, I didn't put any red there. Now increase the load to 20, sigma 0 20, a stress maximum with a stress concentration factor Kt equal to 2, that becomes 40. And when it becomes 40, oops, a little bit of yield there, okay, because S of y is 40. All right, so I got a little bit of the yield there. And so let's put more, we put 30. And then the maximum that it can go is 40 because that's S of y, maybe 41, but not much. And then this yield will increase, right? But that means that under this situation, you can forget about the stress concentration factor because it's not going to happen. Yield is not going to let the stress go further than S of y, or a little bit more if you include hardening, but it's not much. And what happens is that when yield occurs, this plasticity blunts the notch. That means the notch is there, but really is not, because the stress is kept at bay. It cannot grow. Now, of course, if you keep accumulating plastic strain like this, and here you put more, and these two red lines touch each other, that means that you develop a plastic neck there for the entire region, then yes, it's going to break. But as you will see later in the finite element analysis, that is difficult to happen. You're going to have to put a lot of load here for that to develop into a plastic region from side to side, which will cause failure, of course. So this is what is notch blunting, the development of a plastic zone which limits the stress to S of y or heat or something like that. And that way, that means that the stress doesn't grow. Stress concentration factor or not, it doesn't grow. Okay? So here is more proof because, you know, my previous example was made up. And then you say, oh, but he's saying that it's elastoplastic, no elastoplastic, whatever. Okay, this is a real material. This is AISI 1020HR, experimental data that we use in homework 1. Okay, there is no question here, yes? So this is a real material. See, here we have a stress and the applied load, all right? The applied load, I go from 0 to 1,000. So in this is going to be applied to the problem of the bar with the hole that we did in the previous videos. I will show you the result now. So when I apply about 600, I'm a little bit below yield, okay? Now, if the material was elastic, you apply more, then you go on the blue line. Okay, this slope is the real modulo elasticity of AISI 1020, okay? And this is the S of y of 1020 HR, all right? So, okay, now if I put a little bit more than 600, then nothing happened really. Go up a little bit, then just oscillates over here, you see, it's constant. So that's the elastoplastic assumption. It's not applied, but you can see it's good, okay? Because from experimental data, it looks like elastoplastic, yes? And so here we have load, elastic, and plastic. When I go from 0 to 1,000, the stress maximum can go to 434. I don't know if you remember this 434. This 434, it is on the previous video, yes? And so the stress will go to 434, but that is if you keep it elastic. But if you say, no, the material has a yield value, a yield strength, then what's going to happen? When you increase, yeah, it's going to increase, but then immediately at 650, 260, 274, 272, 270, 269, 270, 72, 773. So these are all these oscillations that are going on there, all right? And the yield strength for this material, I think, is 267, something like that. We'll see immediately, okay? So here we go. Oh, okay, it's 264. Yield strength is 264. So you see, I went to 260 with a load that I put on purpose, 600, because 600 takes me to 260. You see there? 260, right there. So to go to 260, I gotta put this particular load, which is just below S of y. So everything is elastic. And of course, with this load that I put 600, the stress here is 60, because remember we have to divide by 10. So stress here is 60. Is that right? Yes, because here the blue, you see this blue, between 44 and 65, it's 60. 600 divided by 10 is 60. And what about here, the green? See if this is the net. Oh, the net should be 120, right? Divided by 5. 600 divided by 5, this is 120. So green, so we go green, and what is my green? My green is there, it's 100 to 130. Yes, you got it, okay? And the stress go to 260. Sure, it shoots from 120 to 260 because KT is 2.2. 2.19 we used in the previous video. So So everything is fine, okay? No plasticity yet, I put here, right? No plasticity, no yield, all right? So, but then I say, okay, crank it up to 620. 620 is gonna take me to 269. But you see, it does not go crazy. It just takes you to 269. And we get this region here. It barely yields, all right? Barely yields. And so then I say, okay, I'm tired of this. I'm just gonna put 1,000. So I put 1,000, the yield is 264, but I don't see the 434. I was expecting, oh man, here's gonna be 434. No, not 434, it's 272. Okay, so what happened with the 434? Before, in the previous video, we have 434. Now we have 272. Well, you know what happened. The material yields, and the notch is blunted, and the stress concentration disappears. Okay? The plastic zone develops, and it's more or less in this red area because that's where we had 272. Yes, it's a small area, so that's why I say that it's hard for this area to propagate to the entire cross section. In which case, yes, if you propagate it, then it will fail. The part will fail. All right, and of course, okay, with the mechanics of material, this is all we can do to calculate the stress, but with the finite element is fancier, so we can do other things. For example, we can visualize in a contour plot the plastic strain. How much plastic strain do we get? Yes. Okay, so the plastic strain will be, I'm hesitant to go back, but okay, I'll go back. Plastic strain will be like this. If you put here a stress and instead of load, you put strain, okay? So it's going like this. And so, okay, but you see here the strain is not it doesn't develop into a big area. It develops only on this, and this here we are at 1,000. Eh? So the plastic strain, this is blue is zero, that's there, it's zero. So that means there is no plastic strain. The whole thing is elastic. And if there is elastic, it's safe. And plastic, plastic is only this tiny bit, and I put 1,000, which is like 400 more than what will take to start yielding. So the notch is totally blunted. It went away, okay? All right, so conclusions for this video. Very important conclusions that we have to remember for next chapters or next topics, fracture mechanics and fatigue. For ductile metals, okay, the material yields at the location of maximum von Mises stress. Okay, sure. With higher load, the stress cannot keep growing at the rate it grows for elastic material. No, you've seen that. It can't. And if you're not convinced, review the videos. Instead, the plastic zone grows, not much. It grows a little bit. And the stress remains barely above the yield strength of the material. You see, barely, okay? So based on this conclusion, stress concentration factors are not applied for ductile metal subject to quasi-static load. This is a big if, because if it's fatigue, yes. So stress concentration factors are applied to brittle material, yes, because they don't yield, so they have to take it. They have to take all the stress with the stress concentration factor fully applied. Okay, but the other thing is stress concentration factors are applied for all material, including ductile, when subject to fatigue loads. Yes, and we will see, in fact, in chapter 6 why this happened. These conclusions are very important for fracture mechanics, chapter 5, where you will see that the stress tries to go to infinity. Okay, that's interesting. And for fatigue, chapter 6, where you will see that, okay, it's complicated. We'll talk about that later, okay? Good, all right, so next lecture will be fracture mechanics, yes. Okay, the videos are here for the students enrolled in the class, and here later when we put them on YouTube. Homework, everybody knows where the homework is, okay? Okay, so I think that's it for now, okay? Fracture mechanics is a topic that I like very much, so I hope to see you soon, okay? Through the next video, okay? Thank you.